Well, this is my lab report on oscillations. So in this lab, I'm comparing the predicted and observed motion of a weight on a spring, then plotting the energy changes over time into a computational model. We're interested in finding out how energy changes over time so we can analyze the work-energy principle and discover any possible energy transfer between the system and the surroundings. For the observed model, we use tracker, and for the computational model, we use closed script to model our data. The fundamental principles in this lab involve Newton's second law, which includes the velocity update formula, position update formula, and the idea that F net equals the sum of all forces, which in this case is the gravitational force and the spring force. We also use Hooke's law, which is that the force of the spring is equal to the spring constant K multiplied by S, the stretch or compression of the spring. Lastly, we use the work-energy principle, which states that the change in energy is equal to the work, in this case change in kinetic energy and potential energy. We also know that the change in potential energy is equal to the change in gravitational plus the change in spring potential energy in this case because we are hanging an object from a spring. Lastly, we know the total change in energy equals 0 when there is no external force acting upon the system. So when analyzing the observational model, I use tracker by plotting change in position over time from the point of release until the end. For my initial conditions, I calculated the spring constant by deriving the equation 4 pi squared times the mass over the period squared. To find the period, I found the average of 3 oscillations from the y direction, which was calculated to be 1.52. After plugging in all the numbers, I found the spring constant to be 7.17. For L naught, I used the given L of 0.7 and subtracted the mass of the object over the spring constant I just found, and I got 0.1506. For my code, I set up the energy equation including 1/2 mv squared for kinetic, mgh for gravitational, and 0.5 ks squared for spring potential, and added these three components together to create my total energy equation. For my while loop, I used elements of Newton's second law and work energy principle to calculate my energy changes over time. So first I found the net force by adding the spring and gravitational forces. Then I applied Newton's second law with the velocity update and the position update formula. Then I updated spring for the loop each time, and finally I calculated my changes in energy that would be utilized in every single while loop. I found that my observational and computational models were very similar. I have seen that in the change in energy, the total energy was consistently 0 because it was the sum of all the energies in the system at each point in time. So in my model here, the red line is the gravitational, the blue line is the kinetic, and the green is the spring. And all the energy components added up is the orange line, which is 0. I noticed that the period is not consistent in the observed model, possibly due to human error in tracking data in the tracker, and also possibly due to air resistance, which decreases the amplitude of the observed model over time. So in the future, if I wanted to improve this, I could potentially plot the points on tracker more accurately, and as seen in the bottom right, there's my model where the blue almost perfect sine curve where the blue line is the computational, the almost perfect sine curve oscillation, and the red model is my observed. As discussed earlier, the energy principle was confirmed in my models because although the values of the gravitational, spring, and kinetic energies were changing constantly while gravitational increased, spring decreased, and vice versa, to ensure the total energy change was consistently 0, since there was no interaction with the surroundings, indicating that energy was not transferred outside the system. Based on the first three oscillations, I found that my y oscillation period is 1.52 seconds, my x oscillation period is 1.61 seconds, and so mass moves more quickly in the y direction due to a period that takes less time than x. The y direction is impacted by the force of gravity, while both directions are impacted by the stiffness and the mass of the object spring. So even without the gravity, the spring will oscillate at the same frequency. However, in the x direction, you have more of the pendulum, while in the y direction, you have more of the up and down force of the spring impacting the movement. Therefore, it is more accurate to use the y direction as the mass of a spring as more directly affected in this experiment. Thank you for watching.